Astronomy is something that's been studied for a long, long time, uh, and particularly the motion of the planets, as many peoples in the past have thought that the motion of the planets had a lot of influence on our lives, uh, and or that the planets were gods or things like or were related to gods or things like that. Um, and so astronomy is something that's been studied for a long time, and there have been many systems throughout the year. A couple of key figures, Ptolemy was a guy back in Egypt who did a lot of studying the planets. He had a geocentric system with the Earth at the center, and then later on, you've all probably heard of Copernicus and Galileo, who believed in a heliocentric system with the sun at its center. Kepler was really kind of the guy who settled, who once and for all settled us into our current understanding of the orbits of the planets and whatnot. One of the big problems that astronomers had with the motion of the planets is that if you track the motion of, say, Mars in particular, but if you track the motion of the planets across the sky, they experience something called retrograde motion. And there are probably some good diagrammatic videos online somewhere. If you Google retrograde motion, you can probably find a good video that will show you exactly what this is talking about. But basically what happens is that a planet, say Mars for example, is moving over the course of days and weeks and whatever, is moving across the sky. One night it's here, next night it's here, and so on. And it goes across the sky, but then it kind of slows down, stops, heads back the other direction, and then loops back around and keeps going, right? And this is ultimately what got rid of the idea of a geocentric, Earth-centered system. Was that if the Earth was the center of the universe, everything would orbit around it, and there wouldn't be these backward sorts of motions. Really, what that comes from is that, say you've got the sun here, and our planet's here, Mars is here. Well, Earth moves around faster than Mars because it's closer, and so as Earth moves, it kind of catches up to Mars and then passes it, and that's when Mars moves backward in the sky. Yeah. Anyway, and Copernicus and Galileo, they had a heliocentric system, but they assumed that the planetary orbits were circles. They were circular. The circle was the perfect shape, or so they thought. And so, if there is this perfect shape, then of course God would have made the universe to function according to circular motion, because it is the perfect shape, and God made a perfect universe. There was this guy named Tycho Brahe, and he was a great observer. He took extremely precise measurements of the positions of the planets in particular, but also the stars and basically everything he could see in the sky. He took extremely precise measurements over the course of years and years and years. And Kepler was his student, and Kepler was the one who ultimately took Tycho Brahe's data and used it to formulate his laws of planetary orbits. But it was only because this data was extremely precise that Kepler came up with the idea of ellipses. That is, Kepler's first law says that the planetary orbits are ellipses. Now, I think I've told you this before, that this may be slightly misleading when you're first taught that the orbits are ellipses back in, elementary school or sixth grade, or I don't know, whenever you do that, because you think ellipse and you get the picture of like, oh, the sun's right here, and so the orbit's like, something like that. But in reality, they are really, really close to being circles. So these guys back in the day that thought they were circles, well, pretty much it looked like they were. So it was only because Brahe's data was so precise that Kepler finally came up with the idea that they were ellipses. Kepler thought they would be circular, and he wanted them to be circular, but he noticed that they were ellipses. And Brahe's data is really pretty amazing. He didn't use a telescope, and for example, Venus has a 1.36% difference between perihelion, which is the point where it's closest to the sun, and aphelion, which is where it's furthest from the sun. Perihelion closest to the sun, aphelion furthest from the sun. Venus only has a 1.36% difference between its perihelion and aphelion. So that's like, if we take this sheet of paper and we say that, the sun is at a point in the center, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There are 30 markings to the end. So that's like saying, if we go 30 times 1.6%, that's 0.48. So like the perihelion's over here, and then, or the aphelion's over here, and then the perihelion is 0.48 of a mark over here. And so it's like noticing the distance, the difference between those is significant. It's pretty incredible that he was able to observe such small differences, using only the naked eye. Anyway, so it's pretty incredible. That's the point I'm making, is that it's pretty incredible that he was able to figure out that the orbits were ellipses from this data that didn't even use a telescope. Now, for all of Kepler's laws, Newton, with the law of gravitation, kind of expanded on and explained them more. From Newton's law of gravitation, we can figure out that allowed orbits are circular. They could be circular, they could be ellipses, they could be parabola or hyperbola. So any of the conic sections work as orbits when you have a orbit governed by Newton's law of gravitation. As I said, these orbits of the planets, if the sun is here, are really, really close to being circles. It's like, maybe like that, where it just comes in a teeny tiny bit off of where here we got a radius of 2 marks, and over here it's just a teeny tiny bit off. So they're really close to being circles. And a circle actually is an ellipse. So Kepler's first law and Newton's laws do allow for circular orbits. So under particularly precise conditions, you could have a circular orbit. So these would be considered orbits, whereas a parabolic and hyperbolic wouldn't really be orbits. It would be like something, say, enters the solar system and then leaves again. Something just comes in from out in space and comes close to the sun and kind of slingshots around it and goes off in some other direction. That would follow a parabolic or hyperbolic path. That's Newton's first law, or Kepler's first law, sorry. Kepler's second law says that planets sweep out equal area in equal time. What that means, sweep out, is that, so say we've got sun right here, and we've got our orbit, and I'll make it an elongated ellipse to, demonstrate the point. Out here, this is a further distance out to where our planet is. So if we say from here to here, some amount of time passes, the area swept out is the area this sector isn't quite, I don't know if you can call it a sector when it's an ellipse, but this sector thing, the area here is the same as the area in an equal time over here, which means that over here, closer to when you're closer, it has to be a wider angle in order to have the same amount of area in the same amount of time, because this part of the orbit is nearer the object. So in that same time, if the times are the same, then the areas are the same. Now, as I've drawn it, the area may not be the same because I just, eyeballed it. But that was what Kepler's second law said, which means a result of that is that planets are traveling the fastest at aphelion and slowest, I'm sorry, that's backwards. Planets travel fastest at perihelion, I apologize, and slowest at aphelion. Yeah. And the same is true of like moons orbiting planets. They travel fastest when they're closest to the planet, which is called periapsis, and furthest at, it's actually aphapsis, I think, which is a really weird word because it has aph twice in a row. And there are another set of words here, perigee and apogee. Para means close. This means closest. Ap means farthest. And then there are different endings that go on that. Helion means sun. Apsis means to a planet. G, like geo, is in reference to Earth. So there are a few different words you'll see in some of the questions on your assignments. So just be aware of that. And because a fun fact that hopefully you know is that the Earth moves the fastest in our winter, well, for the northern hemisphere, because it is closest to the sun. So right about now, actually, the Earth is approaching its closest point to the sun, even though it's colder, because the seasons are a result of how direct the sun's rays are due to the tilt of the Earth. They're not, it's not because of how close or how far away we are from the sun.